Okay, back here again for another chi-squared video. This one is on for data that's formatted in a two-way table. And if you remember the M&M's example, we had a one-way table. We just had a categorical variable, which was the color of the M&M, one of six colors, and then we classified it in terms of one of those six colors. Well, now we have a person, and we're classifying them in terms of two variables. One is the city in which they shopped in. Okay, so this is just some data collected from shopping at secondhand stores. So this classifies them in terms of what city they were shopping in and what gender or sex they were. Now, we're going to find out that we can look at this in a couple of different ways, and it's probably going to be more of a distinction without a true difference. And what I mean by that is, do we want to look at all of this in terms of one population of people classified according to two variables, whether they shop in city one or city two, and the other variable being their gender or sex? Or do we take a look at comparing two populations? One of them is people in city one and one in people city two, and classify them in terms of a single variable. If we look at it that way, that's called a test for homogeneity. And if we look at it in the first way, where we just classify them in terms of one population and two variables, it's a test for independence. So again, it might be a distinction without a true difference. And you'll see that as we move through this, because the process is the same for each of those. But your particular problems that you're going to deal with only look at it in terms of one population accorded or classified according to two variables or a test of independence. Okay, so I'm just giving you the broader picture here of chi-square test and analysis of two-way tables. So now we're going to take the same approach of what we did with the M&Ms, and that is we observe counts, and then we're going to give what we would expect to get if there was no difference between the proportions of people in each of these cities in terms of these two variables. So in other words, here, if I had 106 total men and 353 total women, if I find the percentage of each of those, 106 divided by 459, I get about 23%. And likewise, 353 divided by 459 gives me about 76.9%. With that said, if there was no difference between the cities and the distribution of men and women, then I would expect 23% of these 241. So if I multiply this percentage times this number 241, I would get 55.7. And if I multiply this percentage by 241, I would get 185. And so what that's doing is saying, if I said there was no difference between these two, then what I would expect to get is a breakdown of 55.7 or 185, but really I ended up with 38 and 203. And the same would be true here for city two, only now I'd multiply these percentages by 68 and 150 respectively, the 218. And I would get these numbers. Now, these are run numbers here. Okay. So, in an informal analysis, we would graph these and we could do relative frequencies, which would be the percentage of men and women, or we could do the actual counts. But either way, the bar relationships would be the same. And that's just a Staplett graph. Okay. So this would be the informal analysis. And the formal analysis is we're going to take a look at the chi-squared. This, by the way, these expected counts can be simplified by this formula. And if you look at it, that's exactly what I did, right? If I got the percentage by taking the row total, this green number, divided by the total, and then I multiplied it by the column total, and I got the corresponding expected value in that cell. So doing this for each one of these cells, all I need to do is, again, take row total times column total divided by total to get all of those. And you're really never going to have to do that by, individually, because we're going to see that software does that for us. Okay. Whereas in the one-way table, we had to, for the goodness of fit, we actually had to figure those out, which wasn't really that difficult. Okay. So moving on to through this, just to show you how that works out. Here again, the same scenario here. If you look, and I use some software here, Minitab, notice it's expressing these, and I put these in purple and tried to put these in purple. Now remember, these are rounded, and Minitab is using a more precise way of calculating these. I get 55.66, 50.34, 167.66, and so forth here, which again correspond with these numbers here. Okay. And then what it's going to do is calculate the chi-squared statistic. If you remember, we take the observed count, right? So if I do it just for this cell here to get this 5.601, which again, I'm using some rounded values from over here. These are even rounded values as well. So if I take the observed value 38, subtract the expected, square it, divide by the expected, I get 5.603, which corresponds with this number here. Okay. And then all I need to do is add all those numbers up. So that's what I'm doing here, adding them all up, and I get 15.33. And there's my chi-squared statistic. So again, the thinking and reasoning is the same, only now we're dealing with a two-way table instead of a one-way table. All right. So as I move on here, again, this is just kind of showing you maybe a little bit more detail if I were to do this by hand. And, just here's calculator software, and then the Minitab we already went over on the previous page. Okay. Another example could be this is, the one in which, our reasoning would be a little bit differently in saying, okay, well, now we've got definitely one population, and we're calculating in terms of whether or not this franchise is in an exclusive territory or not, yes or no, and whether or not as it was successful, yes or no. And so if I would just do a couple of the expected counts down here, for instance, if I wanted to know the probability out of that one population, I would select someone that is exclusive. Well, that probability would be, 142 out of 170, right? And then also, if the probability that it was successful, okay, that would be the 123 out of 170. So the probability of them being exclusive and successful, they're independent. We just multiply those probabilities together, and that would give us the probability of being exclusive and successful. And then to get the expected count, I just multiply by the total number of people. So probability of being exclusive and successful times the total people. And if you look at that, I have that calculation here, 142 divided by 170, 123 divided by 170 times 170. And mathematically, I think it's pretty obvious that these, let's say these two 170s cancel out. We are back to column total times row total divided by total, right? Because the 170s or the total totals cancel out. And I could do that again for another one, which I'm not going to do. You can see that here. But I'm just showing you kind of where these things are calculated from. And actually, the calculator is able to do that automatically for you and compute your expected count. So, to run that test on this calculator, this TID3, all I really had to do is put in my observed values, and it'll store the expecteds in this one here, calculate the chi-squared statistic, and actually give us the p-value, which again is just going to be the right-tailed area for that particular chi-squared distribution, in this case, 1 degree of freedom. All right. So again, remember, I'm assuming that you saw the other video when I already talked about the chi-squared distributions. Actually, when we tested equal standard deviations and variances back in week, I think that was week 5, if I'm not mistaken. Okay. And also the previous video. Again, just to kind of get where the degrees of freedom come from, I have a two-way table here. This one would be country of where a person comes from and whether they can. This was an example I've gone over in the past, whether when you do genetics, you can taste the paper, taste bitter, or not be able to taste it. It's based on a gene, apparently. And so here I have actually, notice 8 cells, right? And if I know the row and column totals like I have here, and I just start putting arbitrary numbers in here, let's say 10 tasters from Ireland, if I know I got 10 here and this has to be 783, then this is already determined. So once that's determined, that one's predetermined. And I could do the same if I pick two more of these cells anywhere, the corresponding one is going to be determined by that. Well, if these are already determined and these are already determined, and I know the row totals, then these two are going to be determined. So really, there's only going to be three cells. I don't care where I pick them out of the eight. But once I pick three, all the other ones are going to be determined. And so three vary freely, thus 3 degrees of freedom. And we can always, compute that by just simply taking the number of rows, subtracting one, and multiplying it by the number of columns, subtracting one. Okay, so that's where we know which chi-square distribution to use. And we already talked about these being skewed. And as the degrees of freedom increase, in this case, this one right here would be 8 degrees of freedom. This would be 4 degrees of freedom. This would be 1 degree of freedom. But as the degrees of freedom increase, then the skewness is decreasing, and actually the distribution becomes more like a normal distribution. Okay, so kind of already, went over this. With the men and women, we could look at this as, two independent simple random samples from two cities. Okay, 218 from city 2, 241 from city 1, classifying in terms of men and women. Or we could just look at it as, a test of independence. And that's, what we were dealing with this exclusive territory, just picking stores and then classifying in current terms of two variables. So technically, if we looked at the problem previous just right, we could say that this test of homogeneity could fall within this category also, because the expected counts are computed exactly the same. Here, again, is how we reasoned our way through this particular one, whereas down here, we looked at it in terms of, again, the one sample, okay? So either way, we end up with the same way of determining expected counts, okay? And we're going to call all yours test of independence, okay? Because as I looked in your Alex questions, those are the only ones that they gave you. All right, so for both of these, again, we would write up, again, the hypotheses the same, where the null is always that there's no relationship between these two variables, and that the alternative is that there is, okay? So, like I said, if we go back to this one, we expect, the same percentage of men and women in each of those two cities to be shopping in those stores, okay? So there'd be no relationship between those, between those variables, where there is, and otherwise that relationship might be, more men shop in city 1 at secondhand stores than in city 2, and so forth. Okay, those conditions, or sometimes referred to as assumptions, is that we either have a simple random sample or k independent simple random samples. And, again, you're going to be looking at the test for independence, which would be a single random sample. All the expected counts, just like the goodness of fit, have to be 5 or greater, and that these populations have to be at least 10 times the sample size, which are clearly the case in both of those examples. All right. And so this would kind of be, the one for the stores that we wrote up, whether we use the software or the calculator. Bottom line is we got a pretty darn big chi-square statistic for 1 degree of freedom. And the area to the right of 15.334 is just about 0. So we know there's a very strong, we got very strong evidence to support this alternative, where there is a relationship between gender and location. Now, we don't know what it is based on this statistic. We would have to go back to the analysis and see, like those initial graphs, there's a higher percentage of men and women, in one of the cities than the other. And, maybe if I look back here when we first took a look at that, I'm going all the way back, but you can see in city 1, we have probably about 15% men, where in city 2 now, we have, slightly over 30%. So that would be the relationship. There's a higher percentage of men in city 2 shopping in these stores than women. And obviously the percentage of women is lower now. Obviously, if that goes up, then that's going to go down. Okay. So that would be the relationship. Okay. And we can do a follow-up analysis to be a little bit more particular what the relationship is. Okay. But this is just saying that those differences aren't due to chance. There's something going on there because this probability is so small, right? And so I had a couple more examples here. I don't think I had anything else. Yeah, that we did there. Okay, so that's basically giving you the overview. You are going to again have parts of these problems worked out for you, so it's not going to be that overwhelming for you to do. And but we'll get into, like I said, I just wanted to give you an overview of what these tests are. And we'll go over the specific ALEKS examples here in subsequent videos. So, all right, well, we will see you next video.